Hi, I'm sure most of you guys know me already, but my name is Padia, and I'm an aerospace engineering student at University of California, San Diego, and work with NASA's California Space Grant and bring interesting science and engineering activities for teachers and students like you. Today, can you guys hear me?
Aria, yes. And the only thing I wanted to say was that this group does not know you. So you just introduced yourself, and this is my 5th period Earth Science students now.
Okay, so hello everybody again. Today we're talking to Brian Schwartz. Brian works on the Mars Science Laboratory project as well as on Air Science mission, and we have him here, so I'm just going to pass it to him so he can talk to you, and you can definitely ask questions.
Okay. So we're starting with questions and answers?
Why don't you maybe start with introducing yourself again,
sure.
And maybe a little bit about the project, and then maybe they can start asking questions when they get comfortable.
So hello, thank you for having me. So my name is Brian Schwartz. I'm a telecom systems engineer at the Jet Propulsion Laboratory in Pasadena, California. Recently I was part of the landing team, which helped to land the Curiosity rover on the surface of Mars. My responsibility was to make sure that the telecom system was working so we could monitor Curiosity as she descended through the atmosphere and landed safely. And working with the orbiters we have orbiting the planet Mars, as well as the tracking stations on Earth that listen to the signal. So I've worked at JPL for about 3 years. 2 of those were on the Mars Science Lab. I'm now actually transitioning to a new project called GRACE, the Gravity Recovery and Climate Experiment, so actually right along with Earth science. And we're actually measuring the gravitational field of Earth using 2 satellites in orbit. And what that tells us is by monitoring the changes in gravity, we can actually map how water changes and the distributions of water change around the planet. And that lets us look at how the large-scale climates work. We can monitor the movement of underground water aquifers, because as water moves, the mass changes, and we can detect that from space. And JPL has many missions actually orbiting Earth, as well as other planets. And since JPL has been around, we have sent a robotic explorer to every planet in the solar system at least once, sometimes several. So lots of good science going on, and sometimes the more we learn about other planets, we learn more about our own. And so JPL is very I guess dedicated to both. I think that's a decent introduction. If there are any questions now we're doing?
Let's see.
Brian, it's good to know what we are doing up here at the school is to compare Martian soils with Earth soils. So we're kind of in the mode of looking at differences between Mars and Earth. They have not had any introduction to the difficulty in landing on Mars, things like this. But anything you want to share with us, even how far Mars is away? They think they know it's 1.5 million miles, but that's about it.
Okay, sure. So to give you a little background on, actually we have nice little props, so we can do that. Can they see the whole field?
Yes.
Okay. We're going to do a little camera arrangement. So do a quick introduction to what Curiosity is and how we got to the surface. So we launched on a very large rocket that gets us out of the Earth's gravity and on a course to Mars. We launch sort of behind Mars and are catching up with it. As Mars goes around its orbit, we sort of fall in right behind. It takes 8.5 months from when we launch from Earth to when we enter Mars. Right before entry, descent, landing, or EDL as we call it for short, we're traveling at about 8,000 miles per hour relative to Mars. And we actually, as we get closer to the planet, the gravity field of Mars starts to pull us in. We actually accelerate even more. So right as we hit the atmosphere, we've actually accelerated from 8,000 miles an hour to 13,000 miles per hour. And we hit the atmosphere hard. So this is the entry capsule. So a very small model of one. And so it hits the atmosphere, and the friction of the atmosphere actually will be engulfed in a fireball. The heat chill will reach about 3,000 degrees Fahrenheit as it slows down just by friction, and will slow down from 13,000 miles an hour to about 1,000 miles an hour. And all this time, we're actually steering the rover by firing these thrusters on top to steer the rover to exactly where we want to go. So now we've gone from what we call hypersonic, thousands of miles per hour, to only supersonic, 1,000 miles per hour. We deploy this parachute about 8.5 miles off the surface of the planet. This parachute is actually the material we have here. So the full parachute is about 70 meters in diameter, 70 feet across, big difference. But it's a very, very thin material. There's not a whole lot to it. But it deploys 1,000 miles per hour and whips the vehicle back, experiencing several Earth Gs. So the vehicle has to be prepared to do that, and that'll slow us down, from 1,000 miles an hour to a little slower. And instead of going horizontal like this, we'll actually start to just rotate over as we slow down and start coming more vertical. So once you slow down to about 300 miles per hour, we'll actually deploy the heat shield, which actually does deploy. Packaging peanuts inside. So we'll deploy the heat shield while still suspended on the parachute. We do this about 300 miles an hour. And the reason we do this is because we have a landing radar, which has to look for the ground. It'll help us actually navigate to the surface. So when the parachute or the heat shield gone, still floating on the parachute, doing a little rocking back and forth, the radar will acquire the ground. And when we reach about 1 mile off the surface, going about 200 miles per hour, the rover and the descent stage will actually separate from the back shell, throwing the parachute away. The Mars atmosphere is just too not dense enough to actually slow us down. So we need to use rockets to get us all the way down to the bottom. So we fall out of the air shell. We're traveling 200 miles an hour, and we have 8 we call them Mars landing engines, which it's essentially a rocket pack that sits on top of the rover, and we'll actually move this guy down. So there's a little model we brought along. So the rover sits underneath this giant rocket pack. I don't have one of those, unfortunately. So there's 4 rockets on the side, and it flies the thing down into the surface. With the radar continually looking at the ground and figuring out where it is. Actually, what we want to do is we do a run away from the parachute called a divert maneuver. We're afraid that if we fall out, the parachute could come and be in contact later. So we actually fall out and then fly away, and then come back and then land over there. When we get about 60 feet off the ground, the powered descent vehicle, or descent stage as we call it, will separate, and the rover will be lowered down in 3 ropes while the rocket platform continues to hover. The wheels will deploy, sort of like that, and it'll touch on the surface going less than 2 miles an hour. So gone in 7 or so minutes, we've gone from 13,000 miles an hour to 2 with a nice gentle touchdown on the surface. So it's a very interesting landing system, to say the least. It's definitely the most advanced we've ever tried on Mars before. And it just so happened it worked perfectly. We did a lot of testing, a lot of work, and a lot of very, very smart people put it all together, and it worked flawlessly. As cool as EDL is, the point of what we're doing is actually for science. So we want to know more about the worlds out there. Does life exist elsewhere? Could it have existed even in our own backyard? There are places like Enceladus that have covered by ice, and we think there are liquid oceans beneath them, even bigger than our own oceans on Earth. Liquid water. There's Titan with seas of liquid methane and rivers and everything with complex organic chemistry. Phenomenal places, but Mars is our closest neighbor. It's very similar to Earth. It's a little smaller, it's colder, it doesn't have a magnetic field, but we think there's a chance that it could have once supported life. Missions we've had in the past have shown that at one point it was warmer. There was liquid water sustained on the surface. We've seen evidence of what looks like rivers, river deltas, and we think that at one point it could have actually harbored life. So we are sending missions there to see if life did exist or could have existed in the past. So MSL's mission is to bring this complex scientific package to go look for signs of habitable environments on the planet of Mars. So to do that, this goes into why study Earth, to know about Mars and vice versa. There we have a large team of scientists, not just at JPL, but at universities and other centers, NASA centers around the world. Large teams, hundreds of scientists who are working together to operate this rover and to drive the science we do. And actually, so a year or two ago, I was actually fortunate enough to go on a geology field trip, even adults go on field trips. And we went to Death Valley with a team of students from Colorado. And these were all planetary geologists, which is a very niche field of geology.
They have a geologist there.
Sorry, what's that?
So, Roger, this might be a good time for Nori. There's a USGS geologist there with the kids. So maybe, did you have any questions?
Well,
Well, I brought a microbial mat that I've been growing in my backyard. I got some mud from a wetland that should have cyanos in it. And we always figured that if we're going to get oxygen on Mars so that people can actually live there, we're going to need cyanobacteria. So I wanted the kids to see what cyanobacteria look like, what a microbial mat looks like, and then later on they're going to measure oxygen that's being given off. We're going to take some of the mat and put it into a system where it will be sitting at the window, getting sunlight and giving off oxygen, and the oxygen will displace water in the test tube. So those are the experiments that they're going to be doing.
Excellent. That's very exciting.
Back to you.
We don't have as cool a demo here. I brought some Earth analog rockets with us. And I guess the point I was trying to make was, so we went on this trip with geologists. So I'm an engineer, so my job is to learn how electronics work and how machines work and get them to these cool places. So I wanted a trip to understand more about the science, because I figured the whole point of what we're doing is science, I should know more. And I spent a weekend in Death Valley with these scientists, graduate students and their professors, and we went to all these sites in Death Valley that were Earth analogs. So what that means is by studying features on Earth that look like Mars and understanding the features on Earth, it helps us understand what happened on Mars. So we went to all these different sites and we saw evidence of sedimentary actions of conglomerates. We had pebbles as sort of a cement mixture, evidence of erosion, and by understanding all of these old stream beds and old features on Earth, when we go to Mars and see these pictures, rover sent back of pebbles and stream beds, we can really understand what we're looking at. So there's a lot of value to understanding Earth first before we go to other planets. So there's a lot of people out there studying what's called planetary geology, planetary chemistry, planetary astrobiology, the biology in other systems other than Earth. But all the stars here on Earth. So understanding Earth first before we go out to the heavens. So I'm not a geologist, unfortunately. I pretend to be sometimes, but definitely not an expert. So I will defer to our resident scientist for those questions. But if there are any questions, I'd be happy to take them now.
Does anybody have questions here? They're a little bit bashful, I think, but they did write some questions out. Does anybody have any questions here from yesterday? Brian, can you tell us the one thing that we could not find? We found a minus 125 degrees C as the low temperature. Can you tell us what the hottest it gets on Mars?
I think at the equator it can get to around actually room temperature. I think 25 degrees Celsius. In the summer at the equator. So a nice balmy day on Mars is about room temperature. But I think that's about as high as it goes.
Brian, does that happen at the South Pole also, where there's water on Mars?
So say that again?
Does it get that warm on the South Pole of Mars, where there's water?
No, I don't believe
ice?
So. So we've actually seen, if you look at pictures from orbit, we can see the polar caps, which I think is a lot of it is actually dry ice, carbon dioxide ice. Although there's more and more evidence of water ice as well. But the problem is that, so the pictures we have from orbit, we have orbiters that are taking pictures from space. As the seasons change, we can actually see the ice caps, expanding and contracting. But we still think that, I think the warmer temperature is definitely the equator similar to Earth.
Got it. Okay, so the Earth-like temperatures are at the equator, whereas the potential water, dry ice, or water ice are at the poles.
Right.
Got it. Got it, kids?
So the atmosphere of Mars is very different from ours. So it's about 1/100th of what it is here on Mars. It's very dry. So I'm from the East Coast originally. I moved to the West Coast. One of the things I noticed is that at night the temperature gets a lot colder compared to the day that it does on the East Coast, and the drier atmosphere helps that. So the temperature swings, it can change 100 degrees or more from day to night on the surface of Mars. So even though we may be very, very comfortable if you could breathe carbon dioxide and very little of it, temperature-wise, it would be very comfortable during the day. At night, it can get to incredibly cool temperatures.
Brian, we had a question from one of the students. She's too embarrassed to come up here. Are there seasons on Mars? Very great. It's a great question. Are there seasons?
Excellent. So Mars is inclined just like Earth is, so we're tilted a little bit relative to the plane of the solar system. So as the planet travels around the sun, you have one hemisphere is predominantly warmer than others, so you do have summers and winters, and the sun's lower on the sky. So just like we have shorter days in the winter on Earth, as we also do on Mars. So for MSL or Curiosity, it's a little less of a problem because we actually don't rely on the sun for power. We have this small nuclear power supply that just gives off heat, and we can make energy from that. But our earlier missions, Opportunity, was she's still working and surviving right now and doing some good science. It relies on the sun and solar panels. So in the winter, what they'll actually do is it gets really cold, so it's hard to stay warm because our electronics have to operate, in a certain temperature range. We also have less power because there's less sunlight available. So what they'll do for the winter is they'll actually go into hibernation mode, and they'll drive it up onto a slope, so it's pointed more towards the sun, at the lower horizon, and it'll sit there and just try to stay warm and do nothing except for just try to heat its little electronics and stay warm as much time as it can. And one of the reasons that Spirit died a little while ago was that its wheels or its mobility just got stuck. And it couldn't drive up to that slope. It couldn't get a lot of extra sunlight, and it just got so cold the electronics froze. And when the spring came again, we couldn't contact it, which means it was probably dead. So Opportunity is still doing very, very well. It's also worth noting that even though there are seasons, there's spring, fall, summer, winter, on Mars the year is very different. So one Mars year is about 2 Earth years. So MSL or Curiosity is designed to operate for at least 1 Mars year, so you can see the full climate. But that means we have to operate on Earth for 2 years just because of the time it takes to orbit around the sun.
Okay, Brian, I had another question from another student, and again, too embarrassed, great question though. They found, you found what is called rivers, or I said maybe canals on Mars. Yes. There may have been water there. Where is the water now, do you think?
It's an excellent question. And so there are theories at this point. I mean, one of the exciting things, when I was a student growing up and listening to people, talking about science and technology and space, it was weird because at school you're taught that there's always an answer, we know everything. And I remember asking some very, very smart people what the answer is, and they responded, "We don't know," and that's why we do the things we do. So, it's a long answer to your question. I'm getting there. So we first went to Mars and the surface in the 70s, and we saw a very, very sort of dry, barren area. We lost a lot of interest in it because people thought there were civilizations and everything. And it wasn't until more in the 90s we started sending orbiters again and taking pictures. We could start seeing more. It looked like river deltas and stream beds from orbit. And the more pictures we took and the more missions we sent that are even more advanced, we learned more and more. And we started developing theories about, well, what could this have been, or what is this? And again, looking at Earth as an example, it helps us understand Mars. And it's not until we go to the surface with the Mars exploration rovers back in 2004 and now Curiosity, just recently, where we actually get a chance to go and look at what we see from orbit up close and personal. And so one of the big differences between Earth and Mars, here's the answer coming, is that we live in a giant protective magnetic shield in Earth that protects us a lot from solar radiation. One of the theories is that back in the past, millions and millions of years ago, Mars may have once had a global core, might have had a magnetic field that was a permanent global magnetic field, which would have protected it and allowed the atmosphere to maintain there rather than being blown off by the sun. So just the wind from the sun they think, it's actually slowly eroding the Martian atmosphere. So as the ice sublimates from the carbon dioxide ice or water ice sublimates from ice to air to atmosphere, it's just being blown off the surface into space, and so the atmosphere is getting more and more less dense. So that's one theory. And in 2013, next year, we're actually sending another orbiter called MAVEN, which is going to actually dip into the atmosphere as it orbits a planet and actually measure the atmosphere changes and try to understand the evolution of the Mars atmosphere. But we think that's one of the theories is that there was once a magnetic field, now there's not, and it's being blown up into space. But we don't know for sure, and that's why we're going to send more missions to find out.
That's interesting. I had 2 more questions. One, you had mentioned that there's water under the ground, and another, the students, I have to say this, the student says he has a cold, and I don't think he wants to give it to you. But I probably have it by now. Okay.
But it's true.
So,
we've seen evidence of water ice pretty shallow to the surface, and even lower towards the equator than we ever thought possible. And how we know that, one of the reasons we have a mission called the Mars Reconnaissance Orbiter. It's a very, very large camera, about I think it's like this big around. They can take very quality pictures from Earth. We can actually see MSL on the surface from this camera in orbit. I mean, it's not like, it's a little speck, but you can make out the mast. You can see its shadow from the mast on the surface. And a year or so ago, there was actually a meteoroid impact on the surface that excavated this white stuff around the edge. And the camera showed it one day, and then the next day it was smaller, and the next day it was smaller, and eventually gone. And we have other instruments that can determine what the composition of that is, and they can tell that it actually is water ice. So we just got lucky, a science of opportunity, and nature excavated the science for us, and we saw it from orbit. Because we had missions there, we could see it, otherwise we wouldn't have known. So it was a free. We got lucky. Sometimes we had to work hard for it, sometimes they get us for free, and we get surprised.
Brian, you've been using this abbreviation MSL. What does that stand for?
Thank you. So we speak in acronyms, unfortunately. I try to censor myself, but I don't often succeed. MSL stands for the Mars Science Laboratory, which is now also known as Curiosity. It's its name. But we actually don't name our missions until much later. So for a lot of the engineers who've been working on this for 10 years it took to build it, we call it MSL because that's what we've known for it forever. And it takes a lot of effort for us to call it Curiosity because it's something new. It's like when you get it like someone marries and you get a new uncle. It's weird calling him like. So if I say MSL, it's the same thing as Curiosity. It's a rover that we landed, and remember that it is it's a science laboratory that is able to rove around this region of Mars that helps us understand a lot more about the planet.
Brian, thank you very much. I think we're getting close to the end, but one of the things I as a teacher would like to know is sometimes we get these really interesting questions. Is it possible to email them to either through Kim or to you to see if we can get these answered?
Sure. If I don't know the answer, I work on the hall with some really smart scientists who know a lot more about the surface of science than I do. And I'd be happy to pass along to them, and they're usually very willing to answer questions. So if you have questions, we're more than happy to answer them for you. So talk to Kim, or I guess probably Q's the best person, and she can relay it to us.
Okay, well, we'll do. Go ahead, Kim.
Thank you, Roger.
Class, let's thank him. Thank you so much. Bye-bye now.
Bye.
Bye.